Okay, so this talk is about artificial intelligence planning as applied to multi-operator networks. So, let's see, all right. So planning is perhaps something that not everybody knows about, but everybody knows about machine learning. So planning is another subfield of artificial intelligence, like machine learning. And the viewpoint that one takes in planning is that there is an intelligent agent acting in the world with a goal. So the important thing about the agent is it's what we call its knowledge domain. Sometimes you call it the planning domain. So the knowledge domain consists of a model of the world, which says, let's see, does this thing work? Yeah. A model of the world which describes what kinds of things are in the world. Now, when I say world, it's in quotes because it's not the whole universe, but it's a particular subset, which we will see examples of. Okay, and then the other thing that's in the knowledge model is what can the agent do? What actions can it take? And the last thing, of course, is a goal that the agent has, which is to do something to the world, to put it in a particular state. So now there is a planner, which is an algorithm that defines the appropriate sequence of actions from what the agent can do that leads to the goal. So the planner generates the plan and the agent executes the plan. You can think of the planner as the agent's brain. And the rest of the agent is the arms and legs and so on. Okay, so I want to give you some simple examples of planning problems. So here's a very simple computational problem where the world is simply two variables, x and u. That's the whole world. Okay. And the agent can add 3 to x, it can add 5 to x, it can double x, or it can subtract 1 from x. And the goal is to select a subset of these things in the appropriate order to end up with x equals u, in this case, 17. So, and if you think about it a little bit, one question you may ask is, okay, there are multiple ways of doing this. Perhaps which is the shortest one, which has the fewer steps. Okay, I'm noting that to formulate problems of this kind, there are special purpose languages, one of which is called PDDL, Planning Domain Definition Language. But we are not going to get into that. Okay, so now another planning problem is of a, we can call it a procedural type. So here you have a robot, and it has a table. On the table is a pile of blocks. Okay, and the robot wants to rearrange those to make them look like this. Okay, and okay, so now again, what can it do? It can unstack a block. It can put it on top of another block, or it can take a block from the stack, put it down on the table, or it can pick up the block from the table. Okay. Again, the problem is what is the sequence of actions to do what it wants to do. And now another somewhat similar problem, which goes by the name of the towers of Hanoi, or some people call it the towers of power. So here the problem is that you have 3 pillars, and in the original story there are golden discs on this pillar. But in this version that I'm showing you here, this is a cheap version, so these are wood. So the thing that needs to be done is you can do two things here. You can put one of the disks on an empty pillar, or you can take a disk and put it on top of another stack that's on another pillar, except you can never put a bigger disk on top of a smaller one. So as the story goes, monks have been working on this problem for a while. So now, if you look at the robot arm problem, we can ask, well, what is the length of the shortest plan? We're not asking how to find it, but once you found it, how long do you expect it to be? So with the robot arm, we can see that it's so difficult to see that the length is linear in the number of blocks. However, for this problem, if we have 64 disks, it turns out that the shortest plan has 10 to the 19th actions, which is a big number. If you think in terms of supercomputers, it has 18 hexa actions. And the fastest machine in the world right now does 1 hexa action per second. Of course, if we make the disks 100, things become much more difficult. So now, continuing, what I showed you so far is called classical planning, where if we want to summarize it, the planner is given a goal and has a bag of actions, like a bag of tools. Okay? And it sort of reaches in the bag, pulls something out, says, can I use this? Yes or no? Then it reaches in, picks another one, and so on. Now, there's a development of classical planning, which is called hierarchical planning. And what this does is it takes the systems and it adds something called methods for the planner, and it also substitutes tasks for goals, and tasks sometimes are called high-level actions. So what do the methods do? The methods embody the knowledge of the human domain expert. So if the expert is somebody who knows how to stack blocks, if the expert is somebody who knows how to do algebra, so that's what the methods do. So you can think of them as basically organizing the bag of tools and saying that this tool has to be used with that tool and so on. So it puts structure. Okay, so what the methods do is they take a task, a higher level task, and decompose it in terms of simple tasks. Okay? I will show you an example. And the result is that the search that the planner needs to do becomes much less. So a very kind of trivial example. Let's say that we have the trip planning domain. Okay, where the task is that you want to go from city X to city Y. Okay. So the applicable methods, the ways that you could do this is you could take a plane, you could fly. Now, which of these methods is applicable depends on certain things. It depends on distance, it depends on how much you want to spend, how much time you want to spend, and so on. So now the effect of the method is that when you choose to travel by plane, this decomposes the task of going from CDX to CY into these subtasks. Book the flight, book a hotel, go to the airport, and so on and so on. Right? Now, in turn, each one of these subtasks, for example, go to the airport of CDX, has various methods for accomplishing it. Again, you can take a taxi, you can take subway, you can take your car. Again, which one applies depends on conditions. Okay. So if the conditions are such that you pick one, let's say I go by subway, okay? That again decomposes, that the go by subway method decomposes that task into some smaller tasks. Similarly, for booking a flight. Okay, so that's basically, that's a very simple example of what methods do. And you can think about what you do in your everyday life. Basically, this is the kind of thing we do, except that we don't think about it. We are very smart and we do it without having to think. Now, so that was the introduction to the AI planning field. So we have here an NSF project called Indigo. And what it wants to do is to support establish communications in the situation where there is an emergency, like a disaster, or in the case of something like a military mission. And this network slicing happens in the presence of multiple networks, each one owned by a different operator, and the networks can be in degraded states. So what's good about having an AI planner? Well, obviously it is much faster than a human being. It makes fewer mistakes. It embodies a lot of expert knowledge, and as I will show you at the end, it is a white box. Whereas in deep learning, people spend a lot of effort trying to explain why the box with 1 trillion parameters did what it did. So here things are a little bit easier. All right, so what does the whole setup look like? So you have down at the bottom here the individual networks. Each network is managed by a service management orchestrator, which is called a SMO. Okay. And then on top of these nodes sits a multi-operator SMO, or as we call it, MOS node. All these are very good acronyms, but they sound good. So on top of the MOS node sits the AI planner. And so the AI planner takes tasks or requests from humans that it has its knowledge here, its networking domain knowledge, and it outputs a plan that goes to the most node, and then the most node passes it on to the individual node. Okay. So the AI planner does not try to duplicate any of the functionality that the individual nodes have. So in other words, it doesn't try to micromanage anybody. So what's the planner's knowledge base? The knowledge base is it knows about the geographical region, which is of interest either to the mission or to the emergency. It knows about the capabilities that the individual nodes publish in the areas of mission. It knows the topology of each operator's network, which assumes that what sometimes is called a cooperative context, meaning the operators don't want to keep everything secret, but they are willing to disclose a few things. It has also tasks for the planner, which in this case are creating slices. It has the actions that the planner can take. Most of those are taken from 3 GPP specs. So you can see there, you can create a subnet, notify a subnet, reassign nodes, and so on. And as I said, the planner makes the plan for the task, passes it to the most node forwards it to the operator's nodes, and the point of the actions are they're co-primitive because the individual nodes know how to do them without any further, in order to do this, we need to first do this and then do that. Okay? So they know how to do it. So the final ingredient in the knowledge base is the methods about which we talked about before by example. So again, a trivial example here in this context is to provision a slice, you provision the access subnet, then you provision the transport subnet, then you provision the core subnet. Okay, so the way that the planner basically functions is given a task, it searches for applicable methods. Okay, and it applies them, and if things are successful, at some point every subtask is reduced to what in this knowledge domain is a primitive action, meaning some action that doesn't need any further decomposition. Okay, and like I said before, the effect of the methods is that they take a huge, exponentially big search space and they prune it drastically, so things can work. So here's let's say a small demo. So we have a fictitious island here, which is divided into 7 areas, A1 to A7. And in each of these areas, there are 5 operators that have different presence. So here, and so. And the task is to create a network slice, particular performance that covers these areas that are shown in red. And the networks can be are actually degraded states, so they are famous. All right, so now I will show you, but now there are lots of details about the topologies and the this and that, and exactly what are the failures and which will not be think, which we're not going to go through here. But basically, this is the task for the planner, and the planner creates the 17 action plan. You can look at some of the steps here, and some of them have to do with fixing failures. Okay, so this replaces nodes. This one over here replaces an entire subnet because the failures are too big. There are too many nodes that are failed. So the planner judges that instead of going and fixing every one, I try to replace the whole subnet. Other ones are create an entirely new subnet, and that happens in situations where the parameters that you want the operator doesn't have a ready subnet that can do it, and so on. So the last thing now is that this whole thing, oh, you can't quite see this. So this is white box AI. Okay. So what this means is that once the planner generates a plan, especially if you're a mission commander in the military, you want to know where did this come from. Okay, so that you can have some confidence and see how do we do this. So the planner has the ability to generate what is called a plan tree. So a plan tree is this graph here, where the ovals correspond to methods, and the rectangles correspond to the decomposition that the methods do. So these rectangles are subtasks. In reality, in this picture, every node is labeled with the name of the method and the parameters of the method and the name of the tasks in the parameters. But if you do that, the picture becomes 5 times bigger than the screen. So I eliminated all those labels. But the main thing is that by looking at this and by following the blue arrows, you can see exactly what methods were applied, and the blue arrows take you through the 17 steps of the generated plan. So you can see at every point what method was used, what was the effect of this method, and trace it all the way down. Okay, that's it. Thank you very much.
Question? Oh, I have actually 2 questions. The first question is, you give the input to the planner, you give it the values of your parameters, how does it decide the plan? Is there a training procedure? You think about the plan?
So that,
Mike,
so the planner is basically a search algorithm. Okay, it's a very smart search. Like, it is basically a search. Okay? So it has this knowledge base that says, you give me something to do. I have a bunch of methods that say, if these conditions are satisfied, like we said, when you take a trip, okay, you're gonna go from New York to Los Angeles, okay? Now, okay, you can drive, you can take a train, you can take a plane. Well, since it's far, you probably will take a plane. Okay, so the planner starts applying these methods that take the original task, break it down into smaller steps. Takes each of the smaller steps, tries to see is there some method that applies that, keeps breaking it down until finally it comes down to simple instructions that
Yes.
does that answer?
Yes, it answers. So actually tries different algorithms until it finds
It tries different, yeah, well, the outputs, how you would call them the methods,
Right.
ways of doing
The other question is you say about an SMO and the multi-operator SMO. Is there a software, a specific software that you are using, something open source, something that you are developing?
Open source, yes, something you don't know, because these learning languages are people develop and lots of people remain languages, so they are very sophisticated. So one thing is this PDDL, which is a sort of a standard language for writing language. You can Google it.
Thank you.
Okay, do you take also into account that there may be different plans to achieve the same goal? Like, for example, you may need to perform a feasibility check so that, you know, the plan is viable. And then something may occur during the execution. You have to go back and
So the way that is handled is, okay, this is a kind of a big question, but I'll try to give a good answer. So the planning starts by taking a snapshot of the network. What is the current state of the network, of everybody's network? Okay, so some things are failed, some things are not. Okay, so you take that, you produce a plan. Now, the production of the plan happens in seconds. Okay. So hopefully that is fast enough so that nothing in the meantime changes. And you start executing the plan. But it is possible that as you execute somewhere, something happens and, you know, like you try to open a door and somebody has locked it on the other side. Okay, and you didn't know. Right? So in that case, what you do is you retake a snapshot. You do what's called replan. Start with the new state. That's,
Well, we're gonna have to move on, and there's other things like multi-agent planning too, right? Which is,
I guess multi-agent planning,